we've come to the final lesson on our unit on thermodynamics. And we're going to be talking about a topic that we are not going to really delve much into math. We're going to look specifically from a conceptual viewpoint here at the second law of thermodynamics. Now, something I want to mention right off the bat is that this law, I do not think is that hard to understand. However, fair warning, if you try to find explanations online, they're oftentimes going to be a bit off base. This is possibly one of the most important laws in all of physics, but comparatively, it's also one of the laws that a lot of people explain incorrectly. And that even accounts for a lot of physics teachers, so just be careful. So let's remind ourselves, we have not talked about this law in a really, really long time, way back at the beginning of this unit. So let's remind ourselves how it was historically known. So like in the early 1800s, before we knew molecules were things, what was the second law of thermodynamics thought of as? And it was heat only spontaneously or naturally flows from hot to cold until thermal equilibrium is reached. Meaning, that if I have this system here, let's say they're filled up with two gases, a hot gas and a cold gas, and we allow them, so with some big temperature T, some smaller temperature T, we say that we allow them that there's some permeability here, they can affect each other, heat can go between the two, and as time progresses, we're going to see their temperatures equal out. They're going to reach thermal equilibrium as the heat goes from left to right. In other words, the majority of the thermal energy, the net thermal energy, goes from the hot to the cold, not the other way around. Now, one thing I want to note real briefly is that it is possible to go the other way. It is possible as time progresses to make the hot gas more hot and the cold gas more cold by getting heat to go from the cold to the hot, but this will not happen naturally. We must input energy for this to occur. It is not going to be a closed system. We have to basically interfere with the system to cause this to happen. It is possible. This is basically how, like, a refrigerator works. For instance, you make this colder by essentially pushing heat out. But we had to put energy into that in order for that to occur. Now, to really delve into the second law of thermodynamics, I want to think through a couple of examples of things that we see pretty commonly. First off, imagine we have a glass of water that it's in a room that's at about 293 Kelvin. So it's a room temperature room. It's not very hot, not very cold. And we put, let's say this water is very, very hot. You know, it's basically steaming over here. And we put an ice cube in it. Now, if we were to, let's go ahead and look at an overhead shot of this. And if we were to look at the molecular level here, we would see that the water particles in the hot water have relatively high kinetic energy, so they're moving around fairly quickly at average, a variety of speeds, but overall fairly fast. The ice is at a much lower temperature, so those particles have much smaller kinetic energy. Now, I want to be careful. It's not a gas. So they are bonded together, but they're still vibrating a little bit, and they still have a little bit of kinetic energy, and they're still moving with some little velocity. And we know that as time progresses, so this is like at, for instance, time equals 0, and we know that as time progresses, we're going to see after some time passes that the molecules, the ice has melted, and the hotter molecules have lost some kinetic energy, some thermal energy. The colder molecules have gained some kinetic energy, some thermal energy. And we've reached thermal equilibrium where basically we just kind of have, a nice peak with some in the middle, some faster, some slower, but it's nice and equalized. Okay, but now let's imagine kind of the reverse of the situation. Let's say instead we have room temperature water here. So looking at it at time equals 0, I've got room temperature water, so all the molecules are moving with some average kinetic energy, some faster, some slower, etc. Now, it is possible that these particles in the middle, faster ones could hit slower ones and slow down a lot. And it could be that the particles out here, slower ones could hit faster ones and speed up. And if it happens in just the right way, we could basically end up with this scenario after some time passes. It's possible that these on the outside will be going faster and these in the middle will be going cooler. And in essence, from nowhere, from this room temperature water, we could all of a sudden get a block of ice form in the middle and all the water on the outside be now really hot. This is possible. Now that really hurts your brain a little bit because we have never seen that. You've never had a glass of water just in front of you and all of a sudden an ice cube pops into existence in the middle and the rest of the water gets really hot. Like, that's never something you've observed before. And so let's briefly summarize this. So, if I have this glass of water with the ice cube and the steam, and as time progresses, we regularly have seen that the ice cube melts, the water cools down. So this obeys the law of conservation of energy. The energy has not changed. It's basically been rearranged. Initially, the particles on the outside of the glass had more energy, those in the middle had less, and they kind of equaled out. Admittedly, someone's probably lost the air or whatever, but that's not too important here. And this is a spontaneous process. And remember, what we mean by spontaneous is simply that no work on our part or anyone's part is required for this to happen. In other words, it just naturally happens. If you put an ice cube in hot water, it naturally goes to this more equalized state. It's not very complicated. However, what if we go in the reverse direction? What if I start with room temperature water and I form an ice cube and the water on the outside gets hot? Now, we have never seen this happen, but this still obeys the law of conservation of energy. It's just that now the energy has happened so that the energy of the particles in the middle have gone down and the energy of the particles on the outside have gone up, but the energy is still the same. But this is not spontaneous. We've never seen this happen. We've never seen this naturally occur. But why is it not spontaneous? Because according to the law of conservation of energy, which remember, this is essentially the first law of thermodynamics. The first law of thermodynamics is a restatement of it. But so according to the first law we've learned about thermodynamics, this should be possible. But why isn't it? Now, to explain why we don't see that occur, we're going to have to kind of go in a bit of a tangent. But I promise this is going to come back together. So let's imagine you're standing here, and each hand, or actually, we'll just make it me, We'll say I'm standing here, and I've got 2 decks of playing cards, 1 deck in each hand. And let's imagine that I toss both of these decks up into the air. So 52, 104 card pickup apparently. I throw them in different directions, so that they're separated. And when I do that, let's say that they land, and one of them lands in a pile, and one of them lands perfectly into a fully formed house of cards. Now at this point, you would probably either pay me a lot of money to do it again and or burn me at the stake as a witch, depending, because I think you would agree with me that you've never seen this happen, and this would be unbelievable to see someone throw up all the cards in the air and have them land perfectly into a house of cards. So I want to talk about why we see this one more than we would possibly see this one. Well, let's go ahead and first define what we call macro states. So a macro state is just kind of really it's just the state of a system. But we're going to see why we use the term macro in a second. So one macro state here is a pile of cards. One macro state is a house of cards. Those are 2 different states of this deck of cards. And we could say that looking at these, there are lots of possible microstates or configurations of the macro state of the pile of cards. Like if I take the pile and I jumble them up again and they go back down, you probably wouldn't be able to tell much of a difference. I do it again, I can do it again, and I can rearrange these cards in all of 1,000 different ways, billions and billions of different ways, and there's lots of possibilities that it's going to land in that format. Whereas for the house of cards, there's really fewer possible microstates and configurations. Like, yes, there are many options because I can replace cards with other cards, but they have to land in this perfect pattern, whereas the pile, as long as the pile lands in some pile-like pattern, it's going to be pretty similar. So there are lots of possible configurations for the pile, but fewer configurations or microstates for the house of cards. And what this tells me, and one additional point, there's little information required to recreate a pile of cards. So another way to think about this is that if I told you I made a pile of cards, most of you could probably recreate it within pretty close accuracy with very little information. Whereas if I said, I want you to take a stack of cards and make a house of cards, lots of information is required to recreate that. Like, for instance, how do you know how many of this goes across, how many goes up, how exactly the angle was? So lots more information is required there. But what's more important here is that for the pile of cards, that is statistically likely to occur spontaneously. If I throw the cards up, it is incredibly probable they are going to land in a pile of cards. In fact, it's almost a guarantee. However, if I throw up the cards and they land in a house of card formation, that is statistically extremely unlikely. Almost nil. However, it is technically possible. It is possible that fate, not really fate, but everything could line up perfectly and the house of cards could really fall into place. However, it is practically impossible because it is so statistically unlikely that you could do this, trillions of times and never end up having this occur. So this is an example, or really an analogy for what we know as entropy, which you might be familiar with that term. It comes up in chemistry. So entropy is a measure of disorder of a system. Now, disorder is really how you usually seen it defined. That is not bad, but it can be a little confusing. So instead, I often want you to think about disorder as disorganization or as randomness. So when we say entropy, I want you to think of disorder, disorganization, randomness of a system as a whole. And looking at these two examples, well, which one is going to have more entropy, which means it's going to have more disorder, disorganization, and randomness? Well, this pile of cards, pretty disorganized, and it's pretty random. Like, any of these cards could land any which way and be fine. And so we say this is highly disordered. Whereas if we look over here at the house of cards, it's very organized, it's not very random, and we say it is highly ordered in the sense that everything has to land in a very specific place for this to occur. So we would say that the pile of cards is a high entropy example, and the house of cards is a low entropy example. Now I want to be careful. Some chemists especially don't like this teaching tool, because it sounds like this is entropy really only applies to basically thermodynamics and groups of particles. So these are not groups of particles, so it doesn't really apply here, but it is a good analogy to help us think through this. So let's take this tangent back to what we were previously discussing. How can we connect energy to entropy to try to explain why one of those processes was spontaneous and the other one was not? So let's go back to this. I've got my glass of hot water with an ice cube in it, and I've got a room temperature glass of water. Keep in mind this is a room temperature room, so this is like 293 Kelvin in the room. Okay, so if I was to look at these at the molecular scale, once again, all my hot water, the particles are moving around with a lot of velocity, a lot of kinetic energy. The ice particles are not moving around with much kinetic energy. And in the room temperature example, the kinetic energies have equalized a bit. We have a temperature that's in the middle, and everything, you've got faster and slower, but the average kinetic energy is somewhere in the middle. Now, we already said, as a brief note, looking at this, if I look at the ice, it has a very low internal energy, that the particles, now, okay, I want to be careful there. It has low internal energy with regards to temperature. Technically speaking, there is some internal energy with regards to the bonds that exist between the water molecules. So let's really think of internal energy in this situation as only thermal energy. So the ice has really low thermal energy, and the hot water has really high thermal energy. And if we look at the room temperature water, well, it kind of just has average thermal energy between the two. So if I'm looking at these, my hot and low, so my hot water with the ice cube is a low entropy system. Well, why is it low entropy? Well, we can think of it this way. The energy is less disordered, less disorganized, and less random. Or in other words, it is more ordered and more organized, because I have some of my particles here having one type of energy, and the particles around it having a different type of energy. They are more ordered, and it's hard to think about this because we think of disorder, we often think, okay, well, it's a very chaotic system, but no, we have to think about ordered as in, like we are separating, we are organizing. And so there are fewer potential microstates here, like these hot water molecules. There's a lot of potential options, but really, these particles in the middle, there's only so many ways. They have to be together in certain ways in order for there to be ice. If it wasn't that the case, this would be higher entropy, but if those particles were more close together, we wouldn't have ice, so that's important there. For the room temperature water, this is a high entropy system in comparison to this system, because the energy is more disordered and disorganized, because it has now been kind of equalized throughout, and there are more potential microstates. I could literally move any of these two molecules and have a brand new microstate, and I can do that pretty much any which way, and there would be trillions upon trillions upon trillions of options. So, I now know that it is statistically probable that as time passes, I'm going to have this state go to this state. Because essentially, as time passes, the state is going to, or the system is going to evolve. And it is much more likely that this low entropy system will evolve to a high entropy system because there are just so many more microstates available. The odds that it's going to go in that direction, well, there are so many more possibilities that way that it's statistically likely to occur. Whereas if we go in the opposite direction, it is technically possible. So technically I could say, well, this could go to here. But it is statistically impossible. And the reason why it is statistically impossible is because I have high entropy, and I would have to essentially go to a state where there is fewer possible microstates, and that's just not going to occur, statistically speaking. The odds would be so tiny that you could sit here and watch this glass of water for the entire age of the universe and never see this occur. However, it is still technically possible. So now we're going to create a new formalized version of the second law of thermodynamics. So first off, in a closed system, any spontaneous or irreversible processes always increase the entropy of the system, always increase the disorder. If systems are naturally evolving, if they are occurring with no work from us, they are just going to continue onwards. Now this word here, irreversible, is going to be new to you. So let's talk about what this means. Irreversible means spontaneous in only one direction. So in other words, with the water example, it was spontaneous going from hot water with an ice cube to room temperature water. It was not spontaneous going from room temperature water to hot water with an ice cube in the middle. So it is irreversible because the process will naturally go one way. It will not naturally go the other way. So that is known as an irreversible process. So if our system is closed, anything that occurs naturally will always increase the entropy of the system. So if I have an insulated, remember closed just means it's insulated from the environment, there's no exchange of energy with anything outside, it's going to naturally go to this more disordered, more disorganized, more random state. Now, it gets a little more complicated if we have an open system. So in an open system, meaning that there can be an energy exchange with the environment, with the surroundings, any spontaneous or irreversible processes still always increase entropy. But it could increase the entropy of the system, it could increase the entropy of the surroundings, or it could increase the entropy of both. But no matter what, the amount of entropy still increases. It's either just specifically of the system, specifically of the surroundings, or the two combined. So for instance, if we have some sort of process where entropy decreases. So as a good example, let's say for instance you have a refrigerator. So a refrigerator basically gets colder. So inside that system, the entropy has gone down. However, we exchange heat with the environment. And when that is done, the entropy of the surroundings around the fridge go up. And the fridge would be an open system because we have to put energy into it. Would go up. And the entropy would go up of the surroundings more than the entropy of the refrigerator, the air in the refrigerator would go down. So overall, still an increase in entropy. Now I want to be real careful here because a lot of people think, or a lot of times it'll be expressed as, oh, the system just knows how to increase entropy. Or you might even be thinking, how does it know to do that? And it's just statistics. It's just statistically likely that if you have a macro state with more microstates, that your system is going to evolve to that version, the version with high entropy, than to go from a macro state to a macro state with few microstates, that is low entropy. It's just statistically going to occur. Now, lastly, I want to talk about some consequences of the second law, because there are quite a few and they are pretty impactful. The first one is one we've already kind of talked about, which is that all systems will move toward thermal equilibrium. For instance, if I have this hotter gas in this box and a colder gas in this box, the time equals 0. As time goes on, those temperatures equalize and reach thermal equilibrium because this system here is more disordered or disorganized, because the particles would have, some average, there's more possible microstates for that system than this system, which is way more organized, and that you have hot on one side and cold on the other. Additionally, heat spontaneously, this is the one we already knew historically, but now we can say it a little more firm now, that heat spontaneously flows from hot to cold. Now, as I just said a second ago, we have to be careful here, because when this occurs, the entropy of the hot, piece is actually decreasing, and the entropy of the cold box is actually increasing. So if we were looking at just the system of this box here, we might think, well, wait a second, how is entropy possibly decreasing in this hot box? Because it can't do that. Well, it's an open system. It's touching this part here. So if we want to look at the system as a whole, yes, the entropy of this part goes down, the entropy of this part goes up, but overall, the entropy of the system increases. So the entropy of the cold part is bigger, it gets bigger, then the entropy of the hot part gets smaller. They don't balance out. The increase of entropy is always greater. Another consequence is that no heat engine is 100% efficient. Now remember, we talked about efficiency a long time ago, and efficiency, which we usually just abbreviate with an E, is the energy out over the energy in to a particular system. And what this is telling us is that you will never get all of the energy out that you put in. Okay, so this is a heat engine here. This is kind of what we call a heat engine diagram. So if I look here, this could be an engine of some sort. Like, let's just imagine this is a car engine. Why not? And it has some sort of hot source or heat input. So this would be like, for instance, your spark plugs igniting the gasoline-air mixture, causing the piston to expand. So this would be your heat input, and that goes into the engine, does work. That work is causing the piston to rise, and that piston can be combined to a crankshaft and gears and cause the wheels of the car to turn. However, you're always going to have some waste heat that we say goes to a cold reservoir. Now, this waste heat could be, for instance, part of the exhaust. It could also literally be, if you put your hand over an engine, you can feel how much heat is literally just lost to the environment. So there is always going to be this waste heat. You're never going to be able to get away from that. And so you're never going to have 100% efficiency, because this is required for entropy to go up. This is basically causing at least a decrease, if not at least a no change in entropy, but this is therefore required to cause the system's entropy to increase. But that also means that all energy is going to ultimately go to thermal energy over time. Now, what do I mean by that? Well, if we look at a system here, for instance, imagine the energy contained within the gasoline. Well, that energy has been, basically used up, and a lot of it is wasted away as heat. Some of it went to work. You could do something with the car, but a lot of it is wasted as heat. And once this waste heat is gone, can't really do anything with it. We could try to, but we would put more energy into it than we would get energy out. Same thing with our bodies. We bring in food calories, and a lot of it is burned off as heat that we cannot salvage. So over time, a lot of energy, and specifically all energy, is going to become thermal. And that leads to this idea of the heat death of the universe, that ultimately there's going to be a point when all of the energy goes to a thermal state, and there's no energy useful sources anymore. So the big takeaways for the second law of thermodynamics is, first, can you identify spontaneous or irreversible processes? Spontaneous meaning that there is no work required for it to occur, it just happens naturally, and irreversible meaning that In one direction it's spontaneous, but in the other direction it is not. Can you distinguish between high entropy and low entropy situations? Now be careful. Remember, high entropy means high disorder or disorganization. Low entropy means low disorder or disorganization. It's very easy to get those mixed up. Can we explain how the entropy of a system will change using the second law of thermodynamics, both for a closed system and an open system? And can we at least discuss the consequences of the second law?